So today we're going to start diving into threads. So we already talked about processes, and this is not something new because we all saw that kind of stuff in CS24, and then you got some experience with it, even more experience, I should say, in the command shell project. So you get you have a pretty good sense of that. But now we're going to start talking about threads as pertains to how you implement an operating system that has threads. So processes previously only had one thread of execution, which means you only have sort of one instruction that you're executing at a particular time. But it is becoming really common to have operating systems with threading support. So now I can have a process with multiple concurrent threads of execution, all going at the same time. Or we put at the same time in air quotes a lot of times because it actually is not exactly at the same time, except in specific circumstances. So anyway, but we are starting introducing this notion of concurrency. We do need to change our process model because now that we have multiple threads of execution, not everything can be maintained at the process level. And there's certain things that should be pretty obvious. CPU state. Do I need to be able to have a set of registers for each thread? Well, yeah, that would be really important because each thread may be doing its own thing with the registers, so now we have to have some way of storing registers per thread. What about a stack? Okay, yes, a stack is also another thing that needs to be stored on a per thread basis. So there's certain things. These were the items we had before per process, so address space or page table, some kind of page directory, the program itself, CPU registers, program counter, stack, blah, blah, blah. You can go down the list. And when we move to multi-threaded processes, there's some things we keep on a per process basis. So you can still have one program for the entire process. The various threads share one program. The various threads share the same console and a few other details like that. But then you also have a few details that you factor out for each thread. So CPU registers, program counter, and stack pointer. Those are the things that we have to factor out if we're going to support multiple threads of execution in a given process. Okay? Any questions so far? It's going to get rapidly much more complex than this. Mainly next time. So come Monday, because it'll get pretty detailed on Monday. But there's a couple of reasons why we'd like to have multi-threading. There's a really obvious one and a much less obvious one, unless you've actually tried doing other ways of concurrent programming, and then it's also really obvious. But what's a really obvious reason why we might want to have multi-threaded processes? Anybody here written multi-threaded programs, I hope? Yeah? So, why?
Speed it up.
Speed it up! That's a really obvious reason. And if you look at even just the performance side of things, there's a variety of sub-reasons why we might want to have multiple threads in a program. The second reason, which is much less obvious, is that threading provides a cleaner abstraction than the alternatives, which are grungy and bug-prone, which we will be talking about. When we get to that point, I want to actually talk to you all a little bit more about this to see if you've had experiences with these things as well. Okay, so there's lots of ways that multi-threading can improve performance. One is responsiveness. This is one that we all experience every single day that we use computers, whether you realize it or not. Because almost always we have long-running operations, like downloading the image that goes in this web page, that we'd like to not have to wait till it's finished. And so what we can do is have multiple threads. One that's responsible for doing the slow thing, and then another one that's responsible for responding to the user. So we have a foreground thread for that. We have long-running tasks in other threads that don't hold up the responsive thread, and the user is happy because they do things and the program responds right away. And web browsers are probably the single most common example of this because they have a pretty complex task of rendering a web page. And anytime you visit a web page, you may be downloading anywhere from 12 to 24 different files. And now we have scripts and CSS files. These things didn't really exist when I was first using the web because I started in 1994 and it had just been published in 1993. So we didn't have all those files. We have even more now. And so we have to have ways of managing, accessing all those things and still providing a responsive program. So yeah, user interface thread draws the page, handles mouse clicks, background threads suck stuff off the internet, and then the user interface thread updates as the files become available. So that's generally how these things work. Okay, so given this, here's a question. Does this approach require multiple CPUs to actually get a benefit? I have one foreground thread doing user interfacey stuff, and then I have background threads sucking data off the internet. Does that require multiple CPUs? I'm not seeing any heads nodding. I'm seeing a lot of shaking. Why not? Think about the state of those threads. Yeah, do you?
You can make some of them nicer than others, and some of them run more often.
You could make some nicer than others, but do you need to even? What are those threads going to be doing most of the time? Yeah, they're mostly going to be blocked on I/O. So, that's really cool. Computers and operating systems love threads that are blocked on I/O because guess what they have to do? Nothing. They can just sit there and wait till some interrupt fires, and then I move them out of that queue into the ready queue. So this is really nice. The user interface thread will also almost always be waiting because users are probably the single slowest thing that a computer can interact with. And you think the internet is slow, just wait till you wait on a user. So even with a single physical processor, you get huge benefits, performance benefits, by using multiple threads of execution. And again, this is about responsiveness. We're not really making the entire system go faster, although technically I think you are if you have multiple concurrent operations that you can then parallelize because they, data from different servers or even data from the same server may come in at different rates for different requests, and by overlapping those things, then we can get a huge performance benefit. But this is really more about responsiveness. Now here's another one. We have a scientific or mathematical computation. I have a friend who, when he was in graduate school, was doing molecular dynamics simulations, and he was doing them on a single processor, and he said, I want to make this faster, so he asked his boss for an 8-core system, and he got it, and so he started figuring out how to write a parallel version of his program, and I helped him with a huge chunk of it. We both learned a lot from that experience. But like it says here, instead of performing the computation in a single thread, split it into multiple concurrently executing threads. So again, does this require multiple CPUs to yield a benefit? And if so, why? There's a really easy answer. This is not a complicated question. Why does this require multiple CPUs to yield a benefit? Yeah. They're all doing the same thing, but there's a specific thing that they're all doing, which is using the CPU, right? So if we need to, factor this thing into multiple pieces that are all using the CPU, then clearly we need multiple CPUs to see any benefit. Now, what would happen if we tried to do this on a single processor? Would it run the same speed, or faster, or slower?
Slightly slower.
Why slightly slower?
Context switches.
Yeah, we have additional overhead that we're now introducing. Context switches is one. You probably will have synchronization overhead because almost all computations need some kind of aggregation phase where you combine intermediate results into something that every thread can share. So we get various overheads that start to be introduced. Okay, so this is one of those things that experience with systems programming really helps you to understand the reasons why. I've got an I/O intensive task. Well, probably threads could make it better. If I have a CPU intensive task, then probably threads will only make it better if I have CPUs as well. Okay? Just to give you another example, because I run into this one very frequently, in the CS11 Java track, we have the web crawler, and then we have the multi-threaded web crawler. And even now, it's been 10 years since I've been teaching that track, and you have this web crawler, and you run it on 50 threads. And you see this huge performance improvement, even better than 20 threads and 10 threads and so forth, even if I only have one processor. That's how much we'd like to overlap internet interactions when we write programs that interact with the web. So in those situations, even though you only have one processor, having 50 threads gives you a huge performance benefit. If I was doing a really compute-intensive task, 50 threads would make it much worse if I only have one processor. So it's one of those things. Understanding why that is kind of really important in systems programming. Okay, so here's another. This is sort of a corollary, and it's probably, again, obvious to all of us. So a single-threaded process cannot take advantage of multiple CPUs. If I have multiple CPUs, the only way I can take advantage of it is if I have multiple processes or I have multiple threads running in a single process. There's caveats there too, which we'll start talking about toward the end of the lecture. So you can see that we get scalability benefits from multi-threading. That's another aspect of performance. We already had responsiveness. Scalability is another aspect of this multi-threading that we like to leverage. Okay, now another thing to keep in mind is that we have concurrency and we have parallelism. When we have an I/O-intensive task that we run in multiple threads on a single processor, what we're doing is we're increasing concurrency, but we still have the same amount of parallelism, which is not much. Okay? Concurrency means that you have tasks, different tasks that you're performing at the same time. So their logical control flows overlap. That's all that concurrency is. So you can have concurrency on a single processor system. So yeah, that's what I was just saying. So one CPU system can achieve this by switching back and forth between tasks at appropriate points, ideally when they block, things like that. But concurrency doesn't automatically mean parallelism, because parallelism means I have two things happening at exactly the same time, i.e. I'm running two different instructions at the same time on two different processors, which have a shared memory region that I need to coordinate access to or something like that. So you can see that parallelism introduces fun and new, exciting bugs to solve over concurrency. And typically when you're working on system software that is concurrent and has the ability to be parallel as well, it's a good idea to work on it on a multi-core computer so that you can actually see the bugs due to parallelism as well as the bugs due to concurrency, because they are slightly different. So there's interesting challenges and subtle differences between them. Okay, so that's something important to keep in mind. Okay, so we had our scientific mathematical computation, and we're splitting it into multiple concurrent threads. We'd expect that if we have multiple CPUs, and let's say that we choose the same number of threads as CPUs, or let's say that the number of CPUs is an upper bound on the number of threads we create for our program, these threads will execute in parallel. So they're compute intensive, each one has its own computey thingy, so they can run in parallel and we should see a benefit. Ideally, if we run our program, let's say here it says 1 unit of time to complete on one CPU, and we run it on n CPUs, we should see a speed up of n, or it should take basically 1 over n amount of time that it would have before. Okay, so 1 unit of time on one CPU, 1 over n amount of time on n CPUs. Is this what we see in real life? Only in our dreams, really, unfortunately. This is sort of la-la land. The reason why is because almost always we have some amount of our program that has to execute sequentially. And that sequential part basically constrains the rest of the program to be able to run in an efficient way. Let's say that like 10% of our program was sequential and 90% of it could be run in parallel. What's the fastest we could get that? If we threw like 10,000 processors at it, how much faster would we get it to be? Yeah, 10x is a limit there because 10% of our program is sequential. What if it's 5% of our program that's sequential? What improvement? What's the best improvement we can get there? It's easy, right? Because I just gave you the, 10%. Now 5% would be 20x is the best you get. You run it on 1 billion processors. You're still only going to see a 20 times performance improvement. That's really disappointing. It's kind of in the same way. It's exactly the same as caching performance. If I have like a 95% hit rate on my cache, then my program is still going to run pretty slow if main memory is really far away from the processor. Similarly, if I have a big chunk of my program that's must execute in sequence, and the rest of it can be parallelized, then I have a program that I cannot really improve its performance by running it on many, many processors. Okay? This is actually captured by this mathematical expression called Amdahl's law. Who's heard of Amdahl's law? Okay, a few of you have. I don't know if you heard about it from me. Hopefully not, because it's actually really important nowadays. So you have a task where S is the percentage of the task that can be executed serially. Or like I said, it must be executed serially because it cannot be parallelized. That often happens when people try to parallelize a program. They parallelize it instead. So a single processor machine, the task takes 1 unit of time to run. On an n processor machine, you get this improvement. So you have S, which is the serial part. That's really obvious. Then you have 1 minus S is the parallelizable part over n. That's how much time it'll run. Really obvious expression, right? Well, somebody got their name attached to it. So, come up with simple expressions and you might get your name out there somehow. Okay, so the speed up due to parallelism is just that, 1 over that. Okay, so S plus 1 minus S over n, and then the speed up is 1 over that. So we already talked about a task with 10% that must be run serially. If you put it on 2 CPUs, you get a 1.8x speed up, 3.1x for 4 CPUs. You're already starting to get really sad because you're thinking, wow, all that effort to parallelize my program wasn't very good. 4.7 times speed up on 8 CPUs. And, of course, the fastest you can get it is 10x. And this was kind of the experience that I had with my friend and his molecular dynamics program, because every computation had a big chunk of it that could be parallelized, but then there was a little part of it that had to be sequential. And we saw similar results to this. I'm adding more cores, and it's not going up by n like I wish it would, or being reduced by, divided by n. The execution time's not being divided by n. That's really making me sad. Okay, so people saw Amdahl's law. I can't remember exactly when it was devised. I think it was in the late 70s or the early 80s or something like that. So people saw Amdahl's law, and they said, why do we even waste time and energy on parallelizing computation? Big giant server farms are dumb. Well, what do we do nowadays? We have big giant server farms. Why is that? It turns out that Amdahl's law is a very specific expression for a very specific circumstance, and that's when we have fixed size tasks. Almost always, that is not at all what we want to do. You think about, given more computing resources, I want to increase the size of the task. I'm simulating rocket engine fluid flow because I want to see if my rocket's going to go where I want it to or explode. Which is it? And so if I have 10 computers, I might put my data points in my simulation so and so close together. But if I have 100 computers, maybe I want to have a much finer mesh for my simulation, my fluid flow simulation. I want to do my climate modeling computation. And if I have this many computers, I'll simulate it at this level of granularity. But if I have 10 times the computers, then I'm going to greatly increase the number of data points in my climate simulation. So you can see that when we have more computing resources, we don't hold the problem size fixed. So anybody that says Amdahl's law is the last word on parallel computation, well, in one sense it is, but in another sense it's completely irrelevant, because when we have more computing resources, we always increase the complexity of our computations. Same thing with server farms for rendering movies and stuff. Well, what happens if my server farm gets larger? Well, I increase the quality of my rendering, or I increase the resolution, or both. So it's I make use of that. And so what you notice is that there's a certain characteristic we can take advantage of. As the task size increases, you have the parallelizable part, and it grows at a certain rate, and the serial part grows at a certain rate. So if the parallelizable part grows faster than the serial part does, then the percentage that's serial actually is going down. And so we get a big benefit as we scale up our problem and scale up our hardware. So this is why we do like server farms, and this is why we like to throw large computations at large clusters of computers, because we do see an improvement. We increase the problem size, and we get an increased benefit from parallelizing it by doing so. Okay, and like I say here, this has been formalized as Gustafson-Barsis law. That was late 80s, so this is why I vaguely recall that Amdahl's law was in the early 80s. And people, like I said, got a little bit depressed until they thought about it a little bit more carefully, and they realized, oh, actually, There's a really good reason to keep scaling up our computing resources. Not just physics. Okay, any questions? So this is a pretty important detail here. I just wanted to mention this. Okay, few other benefits, like I say, are resource sharing and economy. So when I have a multi-threaded program for managing resources, then I actually have a benefit over running multiple processes that can't share resources very easily. Threads tend to be much faster to create and destroy. They have fewer resources to allocate and release, so that's nice. Also, context switching between threads in the same process is actually faster because there's certain things I don't have to do. Remember, they share address space. And so if I switch from one thread in a process to another thread in the same process, I don't have to change the MMU's configuration. And if I don't change the MMU's configuration, then I don't have to flush the translation look-aside buffers. And then I get to keep using the fastest cache on the computer. So that's nice. That's a big benefit. Sharing resources between threads is much easier than sharing them between processes. Having done both, I could definitely attest to that. Okay, you just say, here's a pointer, and the pointer means something because you're in the same address space. Processes can't really share pointers very easily. You can open shared memory regions at the same address ranges in two processes, and then you can share pointers as long as you make sure the pointers are only within the shared memory region, but you have to be very careful. So here's the other one, and we're going to spend a little bit of time talking about this, but I asserted that you get a big benefit in the abstraction side of the picture from multi-threading. And we'll explore this a little bit now. An obvious question, you may not have thought of it quite yet, but there's a pretty obvious question when you think about it, which is why are all our long-running calls blocking? You could imagine that you could create long-running calls that are not blocking. You just say, hey, I want to do this thing, and the computer says, no, it's not done yet. Then you say, well, I want to do it now, and it's like, no, it's not done yet. So it comes back right away instead of just blocking and making the process wait. Okay, so why are they blocking? The answer is very straightforward. It's just that blocking operations are much easier to program with than non-blocking operations. But non-blocking operations are frequently still available. The system still frequently makes them available if you would like to use them. So this is the way that we typically use asynchronous operations. You initiate a long-running operation, and then the system says, okay, but then you get to keep running. You don't actually wait until it's finished. And so you come back to the system periodically to say, is it done yet? Are we there yet? Are we there yet? And if you're not, you go do other things. And so when the operation finally completes, you say, are we there yet? And the operating system says, yes, you are. Here's your result. And so you can go on to do the next thing with that particular resource or piece of information that you waited for. Has anybody here written programs with non-blocking operations? Okay, you haven't lived until you've gotten to do that. So maybe set that as a personal goal. I guess you'll get a little bit of experience with that in the operating system, like in the file system lab and so forth. But I'll talk a little bit more about that when we get to a few other things. Okay, so most systems have non-blocking APIs as well as blocking APIs. The most common one is networking. And we'll talk about how to exploit that quite a bit today. But you can also do asynchronous disk I/O. That sounds fantastic. Okay, but you could certainly do that as well. So you have various things that you can do asynchronously as well as synchronously. Another one, another really good example is WaitPid. You can configure WaitPid to be asynchronous instead of just blocking until some child process carks it, Okay, so here's some simple examples. Who here used select? Anybody here use select or poll? What for? You're writing a server. Yeah, that's a very common reason to use select or poll. There's another one called epoll, which is even better on Linux. So like I say, you have a number of file descriptors, and you have a file descriptor set, read FDs, write FDs, accept FDs, and some timeout value if you'd like. And then you have poll, which same thing. You have a collection of file descriptors you can pass it, and timeout if you would like to come back before anything interesting happens. ePOL is similar. So these basically allow you to monitor a collection of file descriptors until something interesting happens or your timeout elapses. And like I say, it returns if a file descriptor can be read without blocking or written without blocking, or if an error occurs and you want to handle the error. Like if you are reading from a network file descriptor, a socket, and the other side closes the socket and you hit end of file. Well, that would be a good reason for select or poll to return. Okay, so you have these various situations that will cause this to return. And applications will use these when they want to take on the burden of implementing concurrency themselves, because they want to get the OS out of the way. We'll talk about some of the benefits and drawbacks. Simplicity isn't always fast, and that's kind of what you notice. You can either be fast and complicated or simple and slow, but easy to get correct. So those are kind of your general trade-offs. And the little parenthesized comment is kind of a huge understatement. So OS has heavily optimized these functions to be fast and scalable. ePOL can monitor a collection of sockets in constant time. So it actually is independent of the size of the collection of sockets. How does it do that? Well, it gets a lot of help from the network card. And so you can ePOL on 100 sockets or on 30,000 sockets, and either one of those operations, it's constant time. Okay? It's not going to scale with the number of sockets. It actually scales with the well, it's just constant time. It's the operating system makes sure it's constant time. Okay, so very, very fast. Okay, so yeah, we'll talk about that in a second. So here's our example. We're going to talk about implementing a web server, because this tends to be where you see these kinds of things. You can do this in a client-oriented mechanism as well. I've had the great delight to be able to do something like that, which I'll hopefully describe in a little bit. But you have a basic sequence of operations for a web server handling a connection from a client. Okay, so I'm waiting. Connection comes in. I receive the request over the socket. What do you want? Oh, you want this file? Fine, I'll serve that file for you. You access the file specified in the request. You pull it into memory, and then you shoot it out the door to the client. Maybe you close the connection after that. Maybe you keep it open so that you can accept other requests from the same client. That's very common nowadays. And we'd like to handle requests as quickly as possible. If we can exploit concurrency, then we'd like to. Because remember, this is I/O blocking, so it's going to be really slow a lot of the time. I'm going to be waiting a lot of the time. Okay? So we have several approaches we could choose from. I have the dumb one, which is single-threaded process with blocking network I/O. You can imagine how popular that server will be. Then I have a single-threaded process with non-blocking I/O, or asynchronous I/O, and then I have a multi-threaded process with blocking I/O. So these are my three options. The single-threaded version, basically think of it as, okay, I get a connection, I listen to what they have to say, I do what they want, I close the connection, then I go and get the next connection. Listen to what they have to say, do what they want, and then respond to that. So you can see that there's basically zero concurrency here. Each request-response cycle is executing in sequence. Well, that's not going to be very fun. Nobody's going to want to use that server. But it is very easy to program, because I have blocking operations. I don't have to think. I can just do a simple loop. You know, accept a connection. What do you have to say? Go get the file. Give back a response. That's really simple to write. I could even do that. Okay? If I have non-blocking I/O and still a single thread, now I can start implementing concurrency so that I actually have multiple overlapping requests, because it'll take a little time for the request to show up, and so-and-so's request may be in the network cards buffer, so I can go ahead and read that out, and I can start sending this file out, but I can't send it all out because the network is slow, and so I can send a little bit of this other file, blah, blah, blah. So you can see that you can start having concurrency with non-blocking I/O, but I still have only a single thread. Okay, so I can start getting concurrency, and what happens is each request response takes the same amount of time, more or less, but the overall throughput will be higher because I'll be able to overlap the flow for each client. So now I'm getting concurrency. I don't even need parallelism yet. I can just have concurrency here, and I get a big benefit because these operations are mostly blocked on I/O, not on the CPU. And from that perspective, you can see, well, the first version, where it's single-threaded process with blocking network I/O, that program is almost never going to be on the CPU. So the OS is going to love it. It's mostly going to be sitting in blocked queues waiting for some device. Our non-blocking version is going to try to maximize its CPU time by doing as much as it can on each I/O operation, and if it can't, it'll just put it aside and come back to it later. So you can see that the second version is going to be more CPU bound rather than I/O bound. Everybody got the concept? Okay, because I'm going to drill into this a little bit because if you haven't written programs like this before, it is a completely different way of thinking about network programming and so forth. So you have many sockets open to many clients. You remember you have some collection of file descriptors for all those sockets. Probably not in an FD set, but you would put them in there so that you could use select or pull, something like that. And for each connection, now you need to keep track of where you are in that interaction. So you start having state associated with each connection. And so you can imagine you pack this into a struct, pack it into a class, choose your poison, what kind of programming language do you like? And you have to keep track of what stage am I at in this interaction. If I'm implementing a different protocol, then I'll need some other thing indicating what stage of the interaction am I in. Okay? That would be just some kind of state value, like an enum or something like that. And then if I'm receiving a request, well, I need somewhere to store it, and so you'll have a buffer. And where I am in the buffer. Have I finished receiving the entire request? You have these kinds of details. So when more data comes in, you can put it in the incoming data buffer at the appropriate location. Okay. If I'm sending the response, same thing. I need the buffer of data that I'm sending out, or I need to know where I am in the file so that I can pull the next chunk of it. And the next time I can send information without blocking, then I'll go ahead and pick up where I left off last time. Okay. So you can see that you have a lot of detail to maintain per connection. And you'll have some giant hash map, or maybe you'll have some giant array, depending on how you construct your program. But each connection has details associated with it so that you can go back and pick up where you left off. This is much simpler in a single-threaded program with blocking operations. The reason why we have all this additional complexity is because we have non-blocking operations. Okay, so the main loop. Wait for some sockets to be active. So the main loop does something really fascinating, which is it waits on all the connections at the same time. And what will happen is some subset of them will become active, which means I can read from it without blocking, I can write to it without blocking, or it has an error state and I can close it or handle the error without blocking. The rest are uninteresting. Okay? So I wait for some subset of the sockets to become active. And then for each active socket, I go through, look up that socket's corresponding state. What am I doing next with that socket? And then I do as much as I can without blocking. And then I go on to the next socket, do the same thing, and go on to the next socket, and do the same thing. Once I've done everybody's work that I can do, then I go back to waiting on everybody again. And what happens is you find that almost every time you finish that loop and go back to wait again, more sockets are ready. So you basically are sitting in that loop handling the subset of sockets that can do things. As you scale up the number of connections that you're handling at the same time, you're spending less and less time blocked on I/O because somebody's ready to do something and you can go back and handle it. Okay? And like I say, the server implements a finite state machine. It ends up looking kind of like this. Obviously, it varies depending on the protocol and the specific thing that you're doing. If you're in the phase where you're receiving the request, you pull the data into the input buffer. If you received it all, then you make a state transition to the next state. Okay? If you're in the send response state, well, push out more data until you've pushed it all out, and then maybe you enter the close the connection state, and so forth. So you have these various details that you have to do to handle each connection. You can see that it's kind of a very different way of implementing things than a single sequential, a single sequence of steps. each blocking operation completes, and then you just go on to the next one. This is much different from that. And if you look at it, the reality is now you are implementing concurrency because you don't want the OS taking care of concurrency for you. Okay? And I say it's complicated, and it is prone to bugs. People still like doing this because it is so much faster. You can make a much faster system doing this than relying on the operating system. But you can see the level of difficulty is quite increased. Are there any questions? Okay. Now, if we have multi-threaded processes, I just got done telling you how it's complicated, but it's faster, blah, blah, blah. Well, if I want to have a simple server, then I can use a multi-threaded process and then have each thread behave exactly the same way as our single-threaded process did. And the OS gets to think about concurrency. I don't have to anymore. The OS gets to think about scheduling or who has to go next. I don't have to. The OS thinks about making sure that the appropriate thread gets waken up and so forth. So the application really only has to worry about the coordination between threads that have shared state. So a multi-threaded web server with blocking network I/O. Hey, guess what? I get to do this exactly the same way as my single-threaded server with blocking network I/O. Receive the request, access the file, send it out the door. Okay. So you can see that multi-threading gives you a fantastic abstraction for achieving concurrency or even parallelism without having to implement it yourself. This is really nice. And so this is why a lot of people like to use multi-threading. Okay? And yeah, if I have a really slow network, then I can start a bunch of threads. And it will probably be fast, even if I'm well exceeding the number of CPUs, because they're going to be blocked on I/O, not on the CPU. Okay? Does that make sense? Okay, so again, when you're evaluating situations where you have these kinds of choices to make, you think about what's most important. Is it most important to get a server implemented with basic concurrency? Well, then you choose the simple way. And if you have to achieve really high performance goals and you can't just throw money at it and buy more computers, then you pick the really fast asynchronous way that's a lot harder to program. And that's what's kind of interesting about this, because I mentioned non-blocking I/O. It is often the fastest way of implementing this stuff. I threw a lot of text up there. So yeah, you basically eliminate a lot of context switching from the the user application into the server. Into the kernel. Because remember, now I have one call to wait for a bunch of connections, not a bunch of threads each doing one call per one connection. So this scales much better with the number of connections. You have reduced space requirements because yes, you have to maintain the state for each thread. Not each thread, each connection, but that means you don't have to have a thread stack. You don't have to have thread context, CPU context per thread or anything like that. So you can actually make this scale really well to very large number of connections. Guys who have used select or poll or things like that, how many concurrent connections did your system support? Did you ever try to max it out? Oh, see, now you're killing me. No? Aw. Okay, so here's the thing. I had to write a program. Let me throw this up here first. Nginx is a really great example of a server that does this. Why did Nginx get created? Well, somebody decided that they were bored, and they thought, I'm going to try to create a server that can handle 10,000 or more concurrent connections. Because up to that point, you might be lucky to have 300 or 400 concurrent connections. And people were like, wow, that's really cool. And so C10K was the way that it was abbreviated. And so they basically tried to come up with a way to scale much better to a really large number of concurrent connections. And it really scales. Like seriously, it's really good. And so it's used by a lot of companies that want to be able to support a lot of concurrent connections at the same time from very large user bases. So the list of companies using it, which is much larger than just this, it is not surprising. Okay? I had a similar experience where I was writing a server. There was a phase where I was really interested in anonymizing proxies, which can be really slow, and so you have a lot of I/O blocking there if you're testing anonymizing proxies. And again, the current, the then current software for doing it would basically run a thread per connection. And maybe you'd be lucky to have 50 connections running at the same time on a client trying to connect to all these really slow anonymizing proxy servers. I wrote a version using asynchronous I/O, and I was regularly running against 30,000 to 50,000 servers all at the same time. Really fast. Okay? So asynchronous I/O is really cool, and I will not retract the statement that you really have not lived until you've gotten a program this way. So hopefully you'll get some opportunity to do it. But like I said, it's harder to get right, so make sure you have the simple version first to fall back on if it's really critical. Otherwise, if it's not so critical, then you can take the time to engineer it correctly, and you can have an unbelievably fast system that scales really, really well. Okay, any questions about this? All right. If you're wondering why I was curious about anonymizing proxies, it was because I was doing some work for a security company, and that was an aspect of their business. So it was really fun to explore. Okay, so let's start talking about implementing threads now, because we have this challenge of how to implement this new facility for our operating system. We need to think about how it works, and we all know from CS24 that it is possible to implement threading entirely in user space. We all love it, right? Yay! Threading in user space. What could go wrong? So you can do it entirely in user mode, but it is challenging for a number of reasons. You can see that our kernel provides processes, and that's all it provides. But our process implements some mechanism by which it can actually have multiple concurrent threads of execution. Okay, so this is nice if we have a system that doesn't actually have multi-threaded processes. So if we have an operating system that doesn't support multi-threaded processes, we can implement it ourselves. Okay, so that's a good thing. It's really uncommon now to have these situations, but if you do, then you can do it. They tend to provide cooperative multi-threading. Remember cooperative multitasking? We have to relinquish the CPU. The reason why this tends to be the case is because when we are in user mode programs, we can't really generate interrupts as frequently as we would like to do preemption. Maybe you're lucky to get every 10 milliseconds. That's like often the fastest you can get the timer to go in user mode. So maybe you're stuck with 50 milliseconds or something like that to keep from putting too much overhead on the system due to generating these timer interrupts and so forth. Okay, so that's not good. And so typically doing preemptive multi-threading on these systems is prohibitive. So it has to be cooperative to make it good. Why would we want user threads in the first place, besides maybe our operating system doesn't support it? Well, even if it does support threading at the kernel level, if you think about it, if I'm staying in user mode, I don't have to actually trap into the kernel. And trapping into the kernel is not the fastest thing we can do. Okay? So if I can stay entirely in user space to create new threads, to destroy threads, to context switch between threads, I don't get the kernel involved at all. The kernel doesn't get any sort of idea like, ooh, you know what, I'll context switch away from you. Well, if you stay in user mode for all of that, then your threading is a lot faster. You're not incurring all that overhead. The issue is, why do we like threads? Well, I like threads because they're a good abstraction if I do blocking operations. And threads are great when I want to run on multiple CPUs. If I do user space threading, I can't solve either one of those problems effectively. This is the issue with user space threading. So I want to use threads to achieve concurrency in programs with blocking system calls. What do I do if I want to do a blocking system call? Okay, so thread N traps into the kernel and says, I want to do something that's long running, and the kernel's like, great, I'll set that up for you, and guess what? You don't get to run anymore. So one thread deciding to perform a blocking system call blocks all the other user space threads. Okay, that's an issue. Also, we frequently would like to take advantage of multiple CPUs. Well, if the kernel doesn't know that you have multiple threads in your application, it can't put you on multiple CPUs. So why would you want to use user threads in the first place? Well, that's a really good question. If you have a lot of threads that are communicating a lot and collaborating a lot, synchronizing with each other a lot, then it might make sense to keep it in user space. But if you have blocking system calls or you have a desire to run on multiple CPUs, it kind of kills user space threading. Okay. So another option, obviously, is to provide some level of kernel threading support, which is thankfully what most operating systems do now. So the kernel can actually be intelligent about doing this stuff. With blocking system calls, no big deal. The kernel will say, hey, you know what? I've got 4 other threads in that same process. This thread just became blocked, but I'd like to give this process more of its time slice, so I'm going to switch to another thread in the same process, and then I don't have to change the MMU configuration. So I save me some time too. Okay, so that's nice. That's one benefit of kernel threading. Parallelism, same thing. This thread will be scheduled on this processor. This other thread will be scheduled on this other processor. Now I have true parallelism. Okay? The drawback is what the benefit was before with user space threading. Now I have to trap into the kernel. And that's slower than just sticking around in user space to do this stuff. Okay, so you can see that there's benefits and drawbacks of either approach. You can imagine that most people do kernel threading because the benefits outweigh the drawbacks. What can you do? Okay, any questions about these two? All right, so since the operating system is what provides multitasking support, there has to be some kind of kernel level schedulable thingy. We call it a kernel thread, which is really confusing because we just talked about kernel threading. Sorry, that's just the terminology. There's a number of places where the terminology is reused. So each thread of a user application must correspond to some schedulable kernel level task, and we call that a kernel thread. So that maintains CPU registers, program counter, stack, all of this kind of stuff. This kernel thread thing is not a process. This will become really obvious when you get into the user mode program support in Pintos. You have a kernel thread, it executes a process. So the two things are paired, but they're not the same thing. The kernel thread is basically the process's representative inside the kernel. So the kernel thread is very lightweight. And kernel threads can become blocked, they can be resumed, and so forth. So we'll talk about the relationship with these between these things much more next time. But we're just sort of introducing some of these concepts. Okay. So we have a kernel thread that is in the kernel. It's a kernel level schedulable task. And then we have threads in the process. So the question is, how do we map threads in the process to kernel threads? And that gives rise to a number of threading models that have been attempted or utilized in various operating systems. So like I said, different threading models have different ways of mapping these user threads to kernel threads. One is called many-to-one, where I have all the user threads in my process mapped to a single kernel thread. Hopefully that's ringing a bell for you. Hey, that's exactly like user space threading, because I have all the threads in the user side of the line, and they all map to a single kernel thread, so the kernel thread represents the process, not the threads, in the user space application. Okay. Like you say here, one user thread decides to perform a blocking operation. Well, too bad. The kernel thread becomes blocked, so all the other user threads are not allowed to proceed anymore. The kernel switches to another kernel thread and allows that process to execute. Okay. Are you guys getting it, I hope? Okay. There actually is a threading library that does this. It's called GNU Portable Threads. And you can see portables right in the name. So this is for situations where you don't have kernel level multi-threading support and you'd still like to be able to write multi-threaded programs. I hope you never find yourself in that world. Threading is not that hard to implement. So if you already are implementing processes, implement threads too. Another approach is one-to-one. So now every user thread in a process is mapped to its own kernel thread. This is identical to the kernel threading approach that we talked about already. Okay, so now I have kernel-supported threading. Each user thread in a process mapped to its own kernel thread. So if one user thread decides to perform a blocking operation, it traps into the kernel. The corresponding kernel thread becomes blocked. The kernel can now switch to another kernel thread for the same process. So another user thread is able to progress while that one user thread is blocked. Again, I hope you guys are seeing. You have user thread, which is like the tip of the iceberg, and then you have the kernel thread, which is the other tip of the iceberg. That was a bad analogy. Anyway, and this is the model that most operating systems actually provide. Like I say, it tends to be the most straightforward to implement to actually provide all of the facilities that we'd like to have. Okay, so those are two. You can probably guess that there's another one somewhere in the middle, right? If I have many to one and I have one to one, well, you can also have sort of a many-to-many threading model, aka a hybrid threading model. And you have some number of user threads mapped to some other number of kernel threads, usually fewer. The idea is that you have benefits from both approaches. User mode threading is really nice because spinning up threads is fast, destroying threads is fast, synchronization between user space threads is really fast. But every once in a while, user threads want to perform blocking operations. So that's where kernel threading is really nice because I can just switch to another user thread. Okay, so if I have these things, so n user threads and m kernel threads, I'd like to somehow map our user threads to our kernel threads in a way that maximizes the system performance so that I can get the benefits and I can have my cake and eat it too, so to speak. So I have a lot of competing, cooperating user threads, then I can map them all to a single kernel thread, and then those threads never need to trap into the kernel because they just keep interacting with each other. Go us. So we reduce system calls and kernel level context switches. And if user threads become blocked on I/O frequently, well then I'll just give it a kernel thread to use all the time. And then that won't hold up other user threads in the same application. Does this make sense? Seems really cool, right? Turns out this is really hard to implement. The reason why is because you have scheduling, thread scheduling, distributed on both sides of this kernel user space line. Becomes a very important line. So like I say, most operating systems just use one-to-one because it's so complicated to get right. Windows 7, for all my whinging about Windows from time to time, it has been really innovative in trying to introduce a hybrid threading model so that they can actually leverage both benefits of both approaches. Okay, so you have threads in the process. Those are user space threads. We have kernel threading support, so we have a couple of kernel threads. And you can see that we have a thread scheduler in user space, and we have a thread scheduler in the kernel. Okay, so they're both making decisions. How do they coordinate? Okay, if we don't have any way of coordinating, then we can't really do this clever thing of mapping user space threads to kernel threads in an intelligent way. I need to know when threads do blocking calls, and I need to know when threads are just cooperating with each other and being really happy together. Okay, so let me see. I'm going to try to spin through some of this because we're almost out of time, or actually we're over time. So yeah, if user thread layer can intercept blocking system calls, then it can actually do some of these things itself. So if I can get a hand in between the kernel and the program, then I can actually handle some of these situations. But if not, then I'm stuck. Okay, also, you'd like to know if the user thread layer can know what the kernel's seeing as far as program behavior. Are things being preempted? Are they being blocked on I/O frequently? So if the user thread scheduler could see what the kernel's seeing, then we could manage this a little bit better. Okay, so let me throw this up there. One of the most common approaches is actually called scheduler activations because what we do is register a callback with the kernel so that when various things happen with kernel threads, we can be informed about it in user space. So this kernel thread was just preempted. Okay, that corresponded to this user thread. Maybe it's really nice, and I can map it to some other. I can share one kernel thread with a bunch of user threads. A kernel thread is about to block, or it's about to become unblocked, and so forth. So now you can start getting a peek into what is happening. We call this mechanism an upcall from the kernel into user space to inform the user program that something is happening that it should care about. Okay, and it calls this thing called an upcall handler, which actually cares. Okay. So yeah, you can read about this. I don't want to take too much time for this. This mechanism of upcalling, again, you're trapping. You're not really trapping in this direction. You're just calling into user space. So you have to change stacks. You have to go through a gate. So it's not literally a trap. It's something similar. It's akin to a trap, but it takes time. And we're also invoking, hopefully, fast code, but we're still invoking more code for scheduling. So you can see that it does affect system performance. Okay, and so you don't see a lot of benefits. You don't see a lot of people picking this up. Of all of the hybrid threading model implementations, about 2/3 of them use scheduler activations. Not a lot of attempts have been made because it's challenging, but of those, most of them use scheduler activations. If you're curious, you can look at the Marcel library, which attempts to use this approach. And that's all I want to say about that. Next time, we'll go ahead and start diving into more low-level details of how kernel threads work. So I'll see you all next week.